It's on.
Hey everyone, I'm gonna get started. So I'm Tim Tully. I'm a partner at Menlo Ventures. The clicker doesn't work. So I'm gonna try to ramp this talk at like 50 slides in like 25 minutes or something. So I'm gonna go pretty fast. So yeah, full of memes today. Hopefully you guys are current on your memes. If you're not current on your memes, you might not enjoy the talk. So that's my background. I worked at Sun Microsystems, worked at this company called iScale. So I could work with this guy, Rajiv Motwani, worked with someone who's sitting in the back. Some company called Pillar Data Systems that got bought by Oracle. I ran engineering at Yahoo for quite some time. Left there to become CTO at Splunk. I ran the product engineering team there for around 4 years, and now work as a VC at Menlo Ventures. This is me as just a snapshot. I still do a lot of stuff with tech and code. I really like hardware, love building server racks and stuff. That's my house on the lower left. Build my computers, do flight simulators, crypto mining rigs, stuff like that. All right, so here's sort of like the TLDR of the talk up front, right? Like, I feel like we're building this modern data stack multiverse, right? There's so many products you can build from so many vendors, and people are building these insane architectures that are extremely complicated with tons of moving parts, right? So they're complicated, they're over-designed, they tend to be pretty expensive, right? Just like the multiverse, if you talk to physicists, they'll say like there's 10 to 500 multiverses in existence, and I think that's like the same number of data stacks that people have running around, because there's like this like combinatorial explosion of possibilities that you could do with modern data stack tools in the cloud. So the way I'm gonna frame the talk is like basically in the essence of like Big Bang and then universal expansion over time, right? So this is like the timeline of the Big Bang. Like I'm not gonna get into time that's like 10 to the minus 43 seconds. It's like way too granular. I'll do it over a longer horizon, so it won't be that. So this is the model for the Big Bang, if you guys are familiar with it, right? It starts with like, this is like this Big Bang start with quantum fluctuations, and you get into the so-called inflation stage. Then you get into like the dark ages with like cosmic background radiation and stuff like that. And that was sort of like the fuel that drives the expansion. Well, it turns out there's similar fuel for the modern data stack as well, which I'll get into. So basically, the evolution of how data has brought us to current state is based sort of on this. And I'll show you how that works. So this is sort of, some people have tried to give this talk before. You'll see some talks online where it's like brief history of data or something, and they tend to be pretty ambitious, and I'm probably no different, but I think mine's more interesting. But this is like the timeline that pretty much everyone shows going back to, say, the 60s, right? You had IBM, IDMS, and then the sort of like the birth of SQL relational models in the 70s. Then you get into like cosmic microwave background, which is really like the first relational databases that were SQL queryable. And then I call it like the dark ages, because I actually did a lot of that, and it was dark, right? It's like Oracle with Teradata and MicroStrategy sitting on top of it. Like that was a bad time to be alive, so it was dark. Then you get into this idea of first stars being formed, right? And I would actually say that that's what I was a part of at Yahoo, right? Where MapReduce came about based on the MapReduce concept from Jeff Dean at Google, which is really just functional programming under the hood. But MapReduce suddenly made it tractable to solve pretty large, historically intractable problems at scale, right? Then there's the birth of like Cloudera and Hortonworks, which are obviously based on Hadoop. Then you sort of like start to turn the corner into like more modern data systems in terms of like how you think about data today, right? So there's Mongo, which is still obviously very popular, same thing as Splunk, Elastic, Snowflake, Couchbase, and then obviously the cloud service providers, right? And so that's sort of like how you start to think about the modern data stack today is really with like these guys, right? And then you have your tools and the pipelines that sort of expanded from that. But now it's pretty wild, right? If you actually look at a modern data stack architecture, there's many, many, many components to it, right? And you're building this like Frankenstein system where you're standing up close to 10 vendors and sort of stitching them together. But what motivated that, right? So if you step back and think about what made that happen, well, it's obviously mobile and the internet, right? It's the idea that everything had to be denormalized, right? Everyone went down that path after exiting MicroStrategy. Then there's like online advertising, right? Suddenly you're collecting data and high dimensionality data from basically everybody on the planet who uses the internet, right? So now you have these massive data scale challenges. Content personalization, right? So Instagram, Facebook, Yahoo, anybody has a feed is just basically doing a ton of machine learning to do linear regression on your user activity. Tons of processing that has to happen there. Then you have this idea around cloud service providers, and that really what that did was level the playing field for everybody. Historically, only big last generation FANG companies could build a system like that, but because of cloud service providers, suddenly everyone could start to build a data company, right? Because you have access to high volumes of compute and storage at a pretty relatively cheaper price. Then you get into the idea of like the data mesh. There's all these data domains, and everyone's generating data or consuming data, and so data is just coming in from everywhere, and then it's being served out to everywhere, essentially. And then there's just too many smart people who wanted to do data, right? So because there's too many smart people, they're building many, many systems, and if you're a good engineer, you're building like really refined tools for very specific jobs because that's what engineers want to do, and suddenly you have this explosion of tools to try to stitch something together. Then there's obviously machine learning, AI data prep, feature extraction, too many great outcomes in public markets where people are building these companies, so it becomes a very attractive proposition to go start a data company. VCs throwing money, not me necessarily, but everyone else, at anything that smells like a big data outcome, like Confluent or Snowflake. I also blame DevOps and CI/CD a bit. The advent of open source, product-led growth suddenly makes it easier to sort of adopt these systems. People suddenly not wanting to be locked in by a cloud service provider and wanting to have alternative solutions like PingCAP. And then smart engineers just trying to refine previously existing solutions to do it one order of magnitude better, or sometimes sub one order of magnitude better. So engineers are just constantly reinventing the wheel, trying to do it slightly better than before. So how did we get to this? Well, just like rewinding back to say pre-Hadoop, let's say. So I was at Yahoo, I was on these teams. We didn't have Hadoop yet. What we were doing was we had MapReduce, but it was written in C++ and Perl. So we had a custom C++ binary that would basically do a join part of a query. And then we had a binary written C++ that would just basically do a massive group by after you sorted the data. So you would basically like sort data and then pipe it into this binary. And you would sort it by key so it could do the massive group by inside of the binary. And then you would glue all that together with Perl, right? And then basically distribute the job. But the data was stored on NetApp filers. NetApp's a company that maybe you're too young to even remember. We were their biggest customer for a number of years. We would store all the data on NetApp filers and then NFS mount the data. But you can imagine if you're doing large-scale processing and reading data off of disk that's remote over the network, you're going to have network saturation pretty quickly. So one of the things we were always doing was like flipping the switch between TCP and UDP constantly, right? Sometimes TCP would be great. Sometimes UDP would be great, but it's unreliable. And you have these like queries that weren't quite complete. It was an unreliable, expensive, and slow system to operate. But the primary thing we hear was cost, right? We're paying these vendors huge amounts of money to basically store data. But then, because that system was prohibitively expensive at Yahoo, the Yahoo search team, which was still really important at that time prior to Google just like taking over the planet, obviously had to query a lot of data inside of Yahoo search logs. And so they thought, well, how do we flip that problem inside out? Well, instead of like moving the data to the compute, suddenly the idea is to move the compute down to the data. But the only way to do that is to actually have commercial off-the-shelf systems where you can store data. So you have to get off of NetApp filers and move to cheap, super micro style systems, right? So that's basically how Hadoop came about, right? Keep that MapReduce paradigm that we had before in C++ and Perl and just flip the problem inside out, right? So they built this system, there's Doug Cutting and all these guys, they built this thing in Java. Java turns out to be a really brilliant decision. Does anyone know why you would write something like that in Java? All right, I'll just answer for you. It's the most accessible language, right? If you could put something in open source and you want people to contribute, you put it in a language that makes it accessible, right? If you write in C++, like, people are not learning C++ really in schools anymore. Like, you're not gonna be able to contribute right away. It's hard to read the code. It tends to be pretty verbose. At the time, it was still STL heavy, so you had tons of like templates and bracket angles. It's just, the compiler errors were unreadable because you get this huge stack trace going backwards that you couldn't unwind. So you write in Java and suddenly more people can start to contribute. And that's probably a lot of what pushed Hadoop and ultimately Spark forward was the accessibility of the code in the open source community. It was a weird time to be alive there. I've told this story at lunch to a few people. I sat in this bullpen with other guys. One of them created Pig. Another guy went to create Hive at Facebook. Turns out I forgot to put it in here, but one of the ClickHouse founders sat next to us as well. I mean, this is like literally in the same bullpen. So really brilliant people walking the halls at the time. And then we started working on Storm and something called Yarn. We were working on something called Apache Data Sketches, which is this stochastic streaming algorithm sort of library. That was all created by us. Then of course you heard from Matei earlier. I've known him for over 10 years. Obvious reasons, like this is 1 to 2 orders of magnitude faster, right? Everyone knows cached partial results, et cetera, et cetera. I think the really key thing for Spark adoption is actually the second one, right? So if you grew up doing Hadoop, the Hadoop programming model actually is really terrible, right? Because you're trying to basically map a complex data logic problem into the MapReduce paradigm, which is really, really hard, right? What Spark did was actually open it up to start to express your business problem in sort of like a more natural way that you would write code anyways, right? You would think about data in terms of sort of almost like arrays, right? And now we have like things like data frame, which is like a much more natural way to think about the problem. Instead of like thinking about input file format and like subclasses of input file format and just trying to like push this square peg through a round hole, which is basically why Hadoop didn't work out. And then obviously having it in Python and Scala makes it much easier to write than Java, which is, everyone knows, it's really verbose object-oriented programming language. And then because Spark is more generalized and say less prescriptive and less opinionated in terms of like how the execution, what you can do in it, right? It took off, right? Because Spark could be sort of more of a processing engine than really an end-to-end computation engine, which is what Hadoop was. So then you have this like landscape. This is Matt Turk. I'll credit him. He's a VC that publishes this pretty much every year. This is the 2012 big data landscape, right? It's pretty accessible still, or at least relatively. And I'll come back to what it looks like now in just a second. So I mentioned this earlier. Cloud service providers, they leveled the playing field. It really made it so anyone could build a company in the cloud, right? You didn't have to have a data center. You didn't have to buy a bunch of gear and rack it up and have people living in the data center to pay attention to the network, putting top of rack switches. None of that has to exist. You buy compute and storage. So I showed this earlier. Now we get like really complicated, right? So if you're building a modern data stack today, this is just like what I could think of off the top of my head. Like, what are the concepts you have to think about if you're an architect at some small to medium-sized company building a modern data stack? It's all of this. Like, if you're not thinking about all of this, you're probably not doing a good job, is my opinion. That doesn't mean you have to take every element and do all of it. But you have to at least reason about it and at least think about what it means to the problems that you're trying to solve. So I would say that's pretty much NP hard. Like nobody can do that in their right mind. It's just, there's far too many moving parts. It's way too complicated. But then there's this guy, Friedman. I don't know if you guys know who this guy is. Man. What happened to American schools? So this is Friedman. He's like a famous physicist that worked with like Einstein in the 20s. And basically he has a series of equations that basically prove that the universe is expanding. The first one that people know canonically is the first Friedman equation, the first one down there, which is like really the simplified version of the equation that's most sort of accessible. So it turns out the universe is expanding, and you have to like go no further than GitHub to really see that, right? Like look at the rate of these data projects over time, right? If you go back to sort of current modern data stack days, which I would say is around here or so, the projects are growing, and there's a few of them, but they're mostly like in here, right? Suddenly, the entire community is latching on to the modern data stack and just growing it, right? And look at it's not a hockey stick. More so as like a vertical slope, right? And then for shits and giggles, we have Hugging Face on there, which is just an insane separate talk on its own. But then look at the attractiveness of the commercial outcomes that you can have by building these companies, right? So this is a plot that one of our great associates that joined Menlo created for us. And by the way, it's an XKCD style, if you guys couldn't tell. So this is a plot of various open source projects with the time that the open core version of the project was created, basically when it was a company built out of it. And then sort of like the current valuations or market caps of those companies, right? So what I'm trying to prove here is it's actually pretty attractive to build a modern data stack company, right? You start an open source project, suddenly it gets at least some amount of traction in the open source community. You build a company out of it, and then look what happens, right? So Hugging Face, well, that's pretty special, but this thing just goes crazy. Preset, obviously, pretty rapid growth, but look at these guys down here, right? Everyone knew what Kafka was, right? But look what happened when they created the company. It took off, right? Because suddenly you have more capital to sort of promote the company, but obviously the open source project, more marketing dollars to put to work, and you can build many, many multi-billion-dollar outcomes by doing this. So the point here is of course people are going to build a ton of companies and a ton of solutions that expands the universe, because you're going to make billions of dollars doing it. But what happened is you land up with this. So this is like the current version of Network's ecosystem or market map. I mean, the same way that I showed that slide earlier that had the bullet points, there's no way you can reason about this market map. There's just way too many vendors, too many spaces. You have to intermix your data stack pipelines with your AI pipelines. There's too much happening here. So more motivational stuff. This is sort of annual spend on business applications. It's just growing really rapidly. You guys can look at the slides offline. This is another slide from Redpoint, who does a great job producing content. This is sort of spend breakdown for cloud data stack solutions over the next 5 to 10 years, and the change in spend over the next 5 to 10 years. So the market's growing. The willingness to buy these products is expanding really quickly. And same thing on the ML side, right? People are basically building parallel pipelines and modern ML stacks, I guess you would say, for data. And so what's happening, right? You guys, I don't know if you guys have seen this movie, Everything Everywhere All at Once. But like that was another multiverse, essentially, right? That's what's happening right now. You're trying to build everything, right? ETL pipelines, ML pipelines. You have to solve governance and compliance. You have to build your data lake or a Delta lake if you're Mate. You have to be on-prem, you have to be in the cloud, you have to be in VPCs. You have to have a bunch of downstream stuff and upstream stuff because the data mesh has to be built now because the media is telling you to build a data mesh. You have to be at the edge. You have to be in every region, every AZ. You have to be low latency. You have to be batch. You have to be full historical. You have to have every iteration of aggregation that exists. And so it's just way too complicated. By the way, you guys know who this guy is? If you don't know who this guy is, I'm going to stop showing you memes. Yes? No? Oh, man, you got it. Stop building modern data stack solutions and watch your memes. That's what I would say. So this is the modern data stack, according to Martin Casado and the A16Z guys. This is a little bit simplified, but the architect in me doesn't like it because there's just way too many boxes, too many arrows going both directions, too many arrows backwards. Like the data architect and the sort of architect in me has sort of an allergic reaction to wanting to build something like this. And it reminds me of this. You guys ever been to Tokyo and ridden the subway? Like you cannot reason about how to go from point A to point B in Tokyo without Google telling you how to do it. Like you cannot read this. I don't even know why they built this map. There's no point. I can't read it. Like if you asked me to find foobar in there, I would not be able to find foobar. It's like, where's Waldo, right? So I'm actually going to argue for the case against the modern data stack. I actually think it's bad for engineers. I think it's bad for a lot of companies because you're going to wind up building this over-designed system that's really, really expensive with too many vendors, right? There's no current standardization on formats or protocols. Most people are probably surrounding themselves with some warehouse type of system that's in SQL. Although I'm at an HTAP conference, I'm a huge advocate for HTAP and what it does, but there are limitations with what you can do with SQL, right? Not every problem in SQL expressible. So if you build your modern data stack, like a lot of the blogs or Medium tells you to build it, you're going to just build the SQL pipeline with things like DBT and others and pre-ETL and reverse ETL. The sort of scope of what you can address from a business problem standpoint is going to be pretty limited because you have SQL, right? And that's why you have a lot of other people like Snowflake and others trying to put Python and sort of execution inside, which I think is pretty smart. It's going to be fragile because you're welding together the pieces. You're going to wind up with quality problems and obviously management problems. And I talked about this. I'm going to talk about the slide. It's actually an argument for using HTAP, but SQL on its own is actually pretty limiting, right? It's this language or DSL, if you will, that came out like 50 years ago, right? And the problems at that time that you're trying to solve were pretty limited. And what is SQL other than a bunch of tables and some keys? And what is a relational model anyways but a graph, right? People have been thinking about graphs for a long time. But doing things that are more complicated like feature extraction or ML data prep is pretty hard if you're limited to just having SQL in front of you. And so the expressibility, the complexity of the problems that you can address is just going to be limited for quite some time. So I'm actually advocating for reducing the modern data stack complexity and actually doing less and sort of coalescing pieces of it so that you have fewer vendors doing a little bit more. And in essence, that's essentially what HTAP is doing, and that's why people are so drawn to it, right? It's because you're basically simplifying life for people. So what is it doing for you? Well, Max gave a great keynote this morning that talked about the benefits. It's just sort of my regurgitation of it here. If you're at an HTAP conference, you probably already know all of this anyway, so I won't recite it to you. It's the illities, right? I asked Andy in the panel about the illities. It's the illities, right? If you're an architect and you're building a system, that's where you start. What are the illities of the system? What are the set of the outcomes that I'm trying to drive towards? And you work backwards from that. I do have a mini rant. I think the same thing's happening in DevOps, right? In the same way that you have this expansion of tools and complexity of CI/CD pipelines, you have infrastructure as code, you have security as code, you have specific companies built to insert themselves into your respective CI/CD pipelines. We're building this sort of intractable system of complexity in the DevOps sort of CI/CD world in the so-called shift left system as what we're seeing in data, which I've been talking about for the last 20 minutes or so. And I call that shift right, but W-R-I-T. So nobody ripped that off. I'm currently writing an article. If I see you with an article today, I'll just point to this video that's being recorded today and I'll find you. So please do not rip this off. If you want to talk about it with me, please ping me offline. I'm happy to have you contribute to this article. Yeah, I'm writing an article. So end of rant, sorry. So in the universe, there's this idea around colliding galaxies, right? So galaxies do collide, right? And so what happens when galaxies collide, right? So they have huge clouds of gas and dust. When they interact and they sort of collide into each other, it sort of gets spawned off. The dust, exhausted gas and dust comes out and it starts to collapse on its own weight and it creates new stars. But what happens is each of the respective supermassive black holes that are at the center of each of those galaxies actually form a bigger, more powerful black hole and sucks up everything. And so what happens is that supermassive black hole that's at the center of those two colliding galaxies will start to sort of go through all the debris that came from that collision and start to suck things into it, right? And I think that's what's happening here, right? And that's why you have this HTAP conference, and that's why it's so well attended, and you get people like Max imitating on stage, is people want that, right? It's happening naturally because the data stack got so complex, right? And there's these mini galaxies that are starting to collide within multiple sectors of the modern data stack. And I think it's already happening. HTAP is that, right? There's the OLAP galaxy sort of ran into OLTP galaxy, and it's forming a bigger galaxy, and that's essentially what HTAP is, right? But I think it's going to happen in a few other places as well. And because now I'm in the venture side, I can make all kinds of predictions that I won't get in trouble for. I don't work at a company like Splunk, and people won't hold me accountable. I can say whatever I want. But I do believe this. Right? I'm not just trying to be provocative. So here's what I think is going to happen. So first is messaging and streaming, right? So streaming is obviously very popular. There's tons of open source projects around it. But there's one in particular that I'm sort of drawn to, and that's Pulsar, right? Because they're combining messaging and streaming into the same system. And ultimately, those kind of go together. And I do think you're going to start to see a little bit of coalescence. The other is sort of the ETL set of galaxies, right? Because ETL has been broken down into many phases. There's pre-ETL, there's ETL, DLT, there's reverse ETL. And to do it the way that it's sort of prescribed if you read popular content is that you have to have all three, you sort of wedge them together and make it work. So the architect in me gets hives from thinking about that. It should actually be one system, right? It's just loading data in, that's pre-ETL. ETL is the actual transformation part. And then the sort of extraction is still ETL, how we did it a while ago. Now there's just specialized companies that do that. And because there's so many vendors in the cloud, you have to have a company specifically to do that because it has to talk to so many destinations, right? Applications and data warehouses are starting to coalesce a little bit. You're starting to see companies like Snowflake think about security problems and think about like, hey, should there be a security application sitting directly on Snowflake? Maybe the same thing will happen to PingCAP as well. And then data discovery, governance, observability, entitlement management, all of that has become separate companies, right? But they logically go together, right? And there's no reason why they shouldn't really be part of the same solution. So So I'll run through two of those and go deeper, right? So here's some popular logos when you think about this sort of set of galaxies that live in this world, right? There's too many tools, it's too granular. The separation of concerns has gone sort of overboard. There really should be one system to think about it. Fewer moving parts so it's more reliable, more manageable, fewer vendors, less cost ultimately, right? Because if you have more vendors, you're inevitably going to spend more money because you have professional services and all these things for each of those vendors. And I talked about messaging and streaming, right? There's many, many solutions. There's historical ones. There's different approaches. Ultimately, what you want to do here is move data from point A to point B and then apply some kind of transformation on it and then send it to different places, right? There's no reason why it should be broken out in the sort of granular way that's happening today. So here's my proposal. Like if I were starting a company today, I would definitely simplify everything. I would not go with that insane set of market maps or the A16Z sort of architecture that you saw. I would actually reduce it down to something like this, right? So there's this concept of the data mesh on the left, which is basically tons of data sources, tons of consumers. That's data mesh, right? They should be pumping that data into some kind of messaging, streaming, queues, topics, whatever it is, move data from point A to point B, maybe does some kind of business logic, does dimension transformation or injection, maybe some light joins. And then it goes into some kind of ETL system where you've collapsed down the pre-ETL, the reverse ETL, and introduced the scheduling and workflow systems, because those tend to be batch systems. So why should a workflow and sort of scheduling not go with it? Should always be sending data to cheap cold storage in the cloud, because in the data world, you want to keep everything, right? You want to be able to sleep better at night by storing literally everything in pretty much every version of it. You want the raw data, you want the semi-transformed, you want the fully baked metrics. All of that should go into cheap cold storage. And then that would sort of reduce down the sort of the back end of the stack to this, right? So definitely, you can guess generative AI is probably coming for data systems where in text, I sort of describe the architecture I want. It runs it through some BERT model, which subsequently gets translated into some kind of infrastructure as code thing that stands up this entire stack, right? That's definitely coming. Because right now, people are thinking about this problem. There's like these data in the box companies. But there's a lot of like mouse, point and click, draws arrow, where you draw arrows and connect things together. There's no reason why a company like this shouldn't exist, where they take like a PRD from some kind of set of requirements and stand up a stack, just based on the PRD. Like that tech exists today. And when you mix the fact that that text exists today with the complexity of the modern data stack, I actually think that's coming. Applications directly connected to the semantic layer that exists on top. Right? Everyone should just sort of standardize as much as possible, speak through SQL, DSLs, REST, GraphQL, that's it, right? There's too many data formats, lack of standardized protocols. This needs to sort of standardize a bit with standardized interfaces. And then I actually think here's where it will remain to be a bit separated out, right? HTAP, data lake, Delta Lake, data warehouses, those can definitely live together. There's a lot of literature, even if you read the PingCAP website, about talking to Snowflake from PingCAP. I'll selfishly push the idea that I think vector search is the future of how search works. We're going to move from sort of text search to semantic search. I have an investment in a company called Pinecone that yesterday announced that they've combined vector search with keyword search to give you better ranking of the vector search. ML model stores, I think, are here, at least for the time being. I'm not going to be that controversial today. I'll talk about that. Knowledge graph databases are growing very rapidly. And the reason for that is because what's the attractiveness? Well, graph databases historically are pretty hard to use. But the business logic needs of the user have grown so much that it makes a lot of sense to pass down those requirements and express them as queries into the knowledge graph, right? So what is this? This is complex business logic on top of a graph database. And then the operational DB, right? You think about how that works today. I think one company that stands out in particular is actually Fauna, right? I think Fauna are the guys that are probably thinking about this the best right now. It'd be awfully hard to collapse all this into one system, so that's why I didn't. Like, this is probably nearly impossible. These are actually really, really hard problems. That's why there's humongous multi-billion-dollar companies doing these separately. So again, same thing's going to happen, right? The same way that I think coalescence for data is coming, I think it's happening in the data side. So I think we've lost the plot. It's too commercially attractive to start many, many companies and break the architecture down into separate companies when you can have billion-dollar outcomes. I think we should have fewer, richer tools and work from first principles going backwards, right? What are the business requirements that I'm trying to drive towards, and then go backwards from that. based on that, what are the architectural requirements I need to solve that solution? And then go backwards from that. What are the system components I need to solve that solution, right? And just really build the architecture that makes sense, not the architecture that you think you're supposed to build because you've been reading too many Medium articles or Instagram posts about modern data stack. And also there's this idea of building things that don't get you fired, right? And that comes from the CIO world. CIOs like to buy tools because they're the logos that people expect them to buy. I think that's actually happening in the modern data stack today. So I think people who are building these systems need to start to think for themselves, right? Working backwards from bullet. If you're a founder and you're starting a modern data stack company and you're solving the coalescence, talk to me. Here's my email address. Yeah, that's it. Any questions? Yep.
Yeah, so why is it simpler to have big systems that solve more problems as opposed to having smaller systems that solve particular problems? Well, I'll give 3 examples. MySQL, MongoDB, and ClickHouse, which all have niches that are pretty well defined.
Yeah, I'm not advocating for collapsing those, right? I mean, that was...
but it's sort of, because I see, yeah, you sort of backed off it a little bit. I'm just curious when you see the
because
yeah, go ahead.
The problem that you're solving to sort of run these queries involves a lot, right? There's query optimization, there's storage, there's scheduling. I mean, databases in a lot of ways are almost like operating systems if you think about it, right? So I think just the complexity involved of trying to merge too many of these together is just far exceeds.
That's exactly what I'm asking.
Yeah.
Because like one of the things I don't understand in that picture, what's the distinction for you between HTAP and data warehouse? Because it gets a little muddy.
Well, we'll see, right? I mean, we're at a PingCAP HTAP conference. We had Matei on stage. Cats and dogs, like I said, are living together on the same stage together. We'll see, right? Because right now, I think about this as transactions and aggregation, right? I don't think of this as transactions necessarily. And there's a lot happening in particular here, right? Over time, you know, there's probably specialized use cases that you do just against this. And then there's specialized use cases where I think you need to have the same data set sitting next to each other without striping it twice and having data skew. So I actually can see a world where they can live next to each other, where I have specialized, say, materialized views here for a certain set of use cases, and then maybe a more generalized representation of the data here that's more accessible for a broader audience.
Because it seems like a lot of the spaghetti in these systems is because you can see, everybody can see and has to operate the connections between these systems. And I think there's an opportunity to, it's not that it matters whether things are complex when you're talking about integration of systems. What matters is whether the user can see.
Well, to my point earlier, somebody may introduce a company here that intelligently knows how to connect these guys together. Yeah. Yeah. Well, that's why there's a box here. Somebody will do this well, right?
Actually, I also have a question about this page. Where is the traditional SQL relational database?
Haven't you guys been talking about that all day here?
that topic today we can see is still pretty big, right? So
yeah, I'm here advocating for you guys. This is the future state. You should subsume a lot of the relational stuff. Yeah. Speak SQL. Yep.
So on the same line, so why do we need to have operational DB if we have HTAP?
You know, a lot of this sort of has a set of complex business logic where I may not want to have it written in SQL, right? So think about like Snowflake and say DBT today, right? Who are a lot of those users, right? It's not necessarily maybe engineers like yourself in the crowd, right? It's a lot of analysts, BI guys, marketing teams, right? So a lot of this, I think, at least in the near term, will continue to be, say, that crowd of customer, right? The people who would use something like this are people who are like literally building applications that have metadata, that have control plane data that needs to be stored. Like you could also use, you know, one of these guys. Matei talked about this morning. But this is really what I would say is like lives in the control plane, lives deeply in the application itself, and it's engineers who would primarily use this, not people who are trying to consume SQL group by aggregations.
Sure, but this is also assumes that operational data is gonna remain operational data. We don't need to do any analysis on top of it. But one day, if we decide to do any analysis, we are back to the old model where we have to move the data into the first disk on the that column. You know, the data warehouse.
Oh yeah, so that could actually happen for sure. I just don't think it's near term. Like if I were to actually build a company today, I would probably build something like this.
Okay.
5 years out, you know, maybe these do merge, right? But for now, you know, this is probably where I would start. Oh, great, Tony. Yeah.
So all these databases, how much of their storage is actually in the cheap storage, and are they going to have like i3, i4 instances with SSDs?
Well, some of the guys talked this morning, right? Everyone basically, like if you're building one of these systems today, and you heard it from Ed a bit, what do? Like conceptually at a high level, right? You're gonna build a serverless system, right? Ephemeral separation of storage and compute. Only keep the last, say, 7 days around in like NVMe or RAM, like near the compute layer. Everything else goes to cold, cheap storage, so S3 Glacier. I mean, that's basically what we did at Splunk. Like, maybe Splunk's a little bit different because it's essentially a time series index, but we knew that people only really cared about the last week at a time. So you could always keep just say the last week at a time hot, and everything else could just go to cold, and then just page it in and out on demand if people need it. And that's basically why I think you need some kind of rehydration system, which I think I have on here somewhere. Yeah. Like that is like how you build a modern database in the cloud. Separate storage and compute, put most of the data in cheap storage, page it in and out if you need it. And all the compute piece should be ephemeral compute, right? So these guys are doing it. PingCAP guys, HTAP is doing it. I can't speak for Snowflake. I know the answer, but I want to talk about it. Okay, Max should ask a question because it's his conference.
Thank you. So since there are a few projects implementing graph database on top of TiDB, which is the storage layer of TiDB. So I was wondering how hard would it be, you know, we integrate graph database with HTAP. Take the right guess. How many engineering resources and how much money we need to make it happen? And also, this is the first question. And the second question would be, I can see there are some, companies are implement a operational DB on top of TiDB. You know, if you are building an operational DB, you need to manage so much metadata, right? You need to do governance, security, and so on. So, what if, is it possible HTAP could be big enough to hold the data of knowledge graph and operational database?
So, I think any further collapse of these is certainly possible, going back to your question further. Present state, I would say maybe, I don't know the exact roadmap of what you have in the back of your pocket, but my guess is at least the next 2 to 3 years, the coalescence isn't quite ready yet. I think what will happen is like, this will start to capture more market, this will start to capture more market, they'll gain critical mass, and suddenly people sort of reduce or want to start to integrate things like this, right? I think to ask people to take a leap of faith where they say, hey, I'm going to collapse 3 to 4 of these things all at once is a bit much to ask of folks, right? But it'll happen onesies, twosies at a time, and then they'll start to grab adjacencies. Yeah. Graph database on HTAP, yeah, certainly possible. I didn't know you were doing that, to be completely honest.
No, we're not doing that. So 3 projects actually build a graph database on top of TiDB. So and also there is a internal hackathon project and want to implement TiDB integrate with graph database. So you can query with SQL to query graph and database, traditional database together. You can use the SQL to join graph database and traditional relational database. It's quite impressive. So I was wondering, just
I mean,
it's not we're going to do it. It's just, Yeah, I'm curious.
I mean, that's certainly possible. I mean, what is a relational model? It's like I said earlier, it's a graph, right? So if you want to translate a query that's like otherwise looks like a graph query down to something that's really the relational model behind the scenes, of course that sort of makes sense. You know, I would say not a lot of vendors have tried to do that yet. Does it make sense from a sort of like design principle standpoint? Of course, yeah, definitely does. You know, with these guys, you know, in particular, I'll just give a plug for one of my investments I'm invested in, or at least Menlo is, called relational AI, right? There's a lot of power in here, right? It's not just sort of like the graph sort of model that's behind the scenes, but it's actually the DSL that they have sitting on top of it that lets you express complex business problems that like subsequently get translated down to a graph query. So, you know, integrating the raw technologies on its own is definitely solvable, but there's a lot of sort of layers that sit on top of it that add more complexity to the problem. Like, I'm not sure you would spend a lot of time wanting to have a custom DSL that, you know, a huge East Coast bank has humongous, you know, scoring models built on that can somehow translate down to a SQL query that you run. Like, I would say in the near term, it's not something I would spend a lot of time on, and sort of let these guys sort of solve that problem. Because there's definitely a market for that.
And actually, I think we are seeing a trend that different kind of database are merged together. Like now, TiDB becoming the building block for another database. Yeah, I think it's a very interesting trend.
Yeah, I mean, that could certainly happen. I didn't say how far out this diagram was, right? But I would say, like, in the near term, this is sort of how I would think about it. If I were to redraw this 5 years from now, maybe it looks very different, right?
Yeah, I wonder if something that will change in 5 years is you have this big assumption about cheap cold storage that everybody. You just said a few minutes ago that that's how you build a modern cloud database. Well, hey, one of the things that strikes me is there's certain operation. Yeah, cheap cold storage is great for long tail, but there's certain things that are just really hard to do. Which, so for example, if you have real-time systems that have high rates of ingest, the organizing of data before you push it to cheap cold storage has to be done on high-speed storage. In fact, the more you can do that, the more performant your systems are. And I feel like one of the gaps that we don't totally cover right now in a lot of the systems being designed is how you get that real-time behavior and still combine it effectively with cheap cold storage.
Yeah, I mean, if I were building Spark streaming or I had Flink sitting in this box, what do? Right? You spool out the sort of exhaust from that data that's being processed in real time,
right, but you have
using a separate thread, right? And then have some background daemon that just does.
This stuff is just incredibly slow. There's a reason that it's cheap.
Right, but what I would do is spool it to disk locally in these clusters, right? And most of those would be like SSDs anyways, right?
Right, so so that means you have basically, you're starting to look like a Lambda architecture where you have sort of like a fast path and you query there and you have to join that against stuff in cold storage.
Yeah, I mean, I'm just talking about exhausting the data. I'm not saying, hey, do this huge high dimensionality join and suck up your dimension tables into the real-time processing. I actually am not a fan of that. I'm actually a fan of denormalizing everything up front. Like denormalizing even at the time of data collection and just pushing it through.
Yeah, I don't dispute that, but I think there's sort of there's a conflict that, well, let's put it this way. I think we're all struggling with it. I work on ClickHouse. We're trying to figure
say hi to Yuri for me. Yeah.
How to deal with this, but one of the reasons that ClickHouse works so well for real-time data is it can take advantage of local disk, and which is the system of record. And so we can merge in there and basically collapse the data so the queries are efficient. It's really hard if you push stuff immediately to cold storage to pull out.
Oh, no, I'm not saying push the data immediately. I'm saying push it out at different stages, right? Push it out at the stage of just collecting the raw.
Right, so
store the raw.
What that means then is there is some storage that isn't cheap cold storage that belongs in this picture.
Where?
Well, that's the question, So
No, I'm not saying there's not. I mean, there is like locally here, like on the nodes, right? Yeah, sure.
Right.
You have local disk. Yeah,
Okay,
so I would
so
spool the data intermediately on local disk and then have some daemon that pushes it out in the background. Like I'm not going to do it in line in the same thread or anything bizarre like that, right? I'm going to try to aggregate it, compress it as much as I can, and mini batch it out. I'm not going to do it in real time.
But you see the point I'm making that you've got high-speed storage, and which has just been sort of perfect. I mean, like anything in the SSD, the fact you can get it in the cloud has sort of altered the mathematics experience of building real-time systems, because you have this incredibly high performance storage, and it doesn't perform at the speed of memory. So the question is, where does that fit in this picture? That's a fundamental capability.
Well, I mean, there's
that we're-
I don't know the exact underpinnings of what Max and Ed have here, but I suspect there's multi-layered storage, right? There's like probably an NVMe cache in here somewhere. Am I wrong? Am I right? Right? And then there's SSD. It's tiered storage, right?
Right.
Everybody should have tiered storage.
Okay.
Yeah. But ultimately, it should go here.
You figure
Yeah.
it's fine. Okay,
Yeah.
maybe it's me not understanding.
Yeah, I mean, I didn't draw. I mean, I could expand this box in some other talk, but yeah. Yeah.
And the comment real quick on the HTAP aspect, and we'll take it full circle. But what we're experiencing sort of is really at the level where you have a mixed workload that anywhere from 10% to 40% analytical workloads. Anything beyond that, then from a cost and performance perspective, it doesn't really make sense. So I think, from an experience perspective, that's what we're seeing right now.
Interesting. Okay. Cool. All right. Thanks, guys.